Notes for section 3.2, linear functions. This will be part 1 and 2. So for our key vocabulary, in mathematics, when we refer to a line, it is always defined as linear. Saying a straight line is redundant because lines are always straight. If we want to describe a graph that is not straight, that is called a nonlinear function. Linear equations in two variables. A linear equation in two variables, x and y, is an equation that can be written in the form y equals mx plus b, where m and b are constants. Linear function is a function whose graph is a non-vertical line. And finally, nonlinear functions are functions that do not have a constant rate of change, so the graph is not a line. Key ideas. Identifying linear functions. In example 1, we need to find out if the graph represents a linear or a nonlinear function and explain. So when you look at graph A, is that a straight line? And the answer is no. So A is nonlinear because it's not a straight line. Letter B, when you look at letter B, that is a straight line, so that function is linear. So write down nonlinear because it's not a line under A, and linear because it's a line under B. To make it harder, we are going to figure out if a function is linear or nonlinear from a table. So here it's not as obvious. The way we determine if it's linear or nonlinear from a table is to figure out the rate of change. The rate of change is also known as your slope. Okay, so m, which is your slope, also known as your rate of change. So for the first table, letter A, our change in x is 3 every single time, plus 3. We're adding 3 every time the number changes in the x row. For y, the first time from 36 to 30, we subtract 60. 30 to 24, subtract 6, not 60, I apologize. And then 24 to 16, subtract 6 again. So the rate of change is the change in y over the change in x. So for letter A, change in y is always -6 over 3, which means your rate of change is -2. And since your slope, your rate of change is constant, it is always -2, you have a linear function. Linear because the rate of change is constant. Let's look at table B. When we're looking at the change in x, I see that x numbers are going up by 2 every time. And the y numbers, the first change is adding 7. The second change is adding 11. The third change, it adds 15. So your slope, or your rate of change, is not constant. First time it's 7 over 2. Then it's 11 halves. Then it's 15 halves. So since the rate of change is not constant, that means if you were to graph this, and I'm not going to be perfect, but if we started here, if we went up 7 and then over 2, you could be like right here. And then the next time you go up 11, so a little bit more than 7 and then over 2. So this part would be a little bit steeper. And then the next part would go up 15 and then over 2. So it'd be even steeper there. So it's not straight because your slope, rate of change, is changing. So nonlinear because the rate of change is not constant. On the next page, I would like you to decide on your own if the graph or table represents a linear or nonlinear function. Pause the video, answer the questions, and then when you're done, check your answers. Here are the answers you should have come up with. Letter A is linear because it's a line. Letter B is nonlinear because it's not a line. C is linear because it has a rate of change that is constant. And D is nonlinear because the rate of change is not constant. Example 3. An equation describes a linear function if it can be written in the form y equals mx plus b, where m and b are constant. Which of the following equations represent linear functions, and explain? So y equals 3 and 8/10. This might not seem like it is in the form of y equals mx plus b, but technically you can just write y equals 0x plus 3.8. And the m is 0, the b is 3.8, because anything times 0 is 0. So we could just rewrite this as y equals 3.8, which is that equation. For the next one, y equals the square root of x. This cannot be written in y equals mx plus b form. Technically, this could be written as y equals x to the 1/2, but still that is not a straight line, it's nonlinear. Y equals 2 minus x. We can just rewrite this as put the negative x in front and the positive 2 in back. And if you need to see it this way, this would be y equals negative 1x plus 2. So your m would be negative 1 and your b would be 2. They're constant. This y equals 3 to the x power. Anything raised to the x power or raised to a power is not going to be linear. So nonlinear. And I should actually write that under here too. Circle and then write it in there, nonlinear. And then for this one, it is linear. And this third one was linear. All right, let's look at the fifth one. We have y equals 6 times parentheses x minus 1. Well, if I were to distribute the 6, I can rewrite this as y equals 6x minus 1, or I'm sorry, minus 6, where my m is 6 and your b is negative 6. In the form of y equals mx plus b, it's linear. Therefore, we are good to go. And the last one, if we were to solve and get y alone, yes, you can subtract and divide by 1, but still y equals negative x squared. You have a power in there, and that's nonlinear. If you have it raised to a power, it is nonlinear. All right, on your own, pause the video and decide for letters A, B, and C if they are linear or nonlinear. When you're done, check your answers. Here are the answers you should have come up with for the on your own section. Graphing linear functions. We have discrete domains and continuous domains. Discrete domains, if you look at the example on right here, you'll see that you have a set of numbers, or I'm sorry, of input values that consists of only certain numbers. So we have 1, 2, 3, 4, 5. If it's a continuous domain, we start at 1 and go to 5, and it consists of all the numbers in this interval. So even 2.5 or 3.25 or 4.75, all the numbers are part of this domain. Whereas this domain, it's only 1, and then only 2, and then only 3. So that is a discrete domain versus continuous domain. Example 4, graphing a linear function in function notation. The linear function y equals 15 and 95/100ths x represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. The first thing we're going to do is find the domain of the function. Is the domain discrete or continuous? So first, let's identify what the domain is. So the domain is our x values, and x represents the number of tickets. So I would write down all this information. So is it discrete or continuous? Discrete means that it would be just the integers. So is it possible that we could only buy one ticket or two, three, four? Or is it continuous where we could have 1.5 tickets or 2.5 tickets? And so your answer you should come up with is discrete, because you cannot buy a half of a ticket or a fraction of a ticket. So you cannot purchase a fraction of a ticket. All right. Graph the function using its domain. So when we buy, if we're going to use this equation, y equals 15.95x. If we buy 0 tickets, we are going to spend $0. If we purchase 1 ticket, x would be 1. We would multiply that by 15.95. Our cost would be $15.95. If we purchased 2 tickets, you'd multiply that by 2 and you would get $31.90. If you purchased 3 tickets, 3 times 15.95, you would spend $47.85. And 4 times 15.95 gives you $63.80. Ordered pairs are just x, comma, y. So the first ordered pair would be 0, 0. The second ordered pair would be 1 and then 15.95. Your next ordered pair would be 2, comma, 31.90. Then you'd have 3, 47.85. And finally 4, comma, 63.80. If we're going to graph this information, first of all, our graph is pretty small. So I'm going to zoom in. On the x-axis, our domain, we go from 0 to 4. So for this, I'll start 0 here, and I'll actually spread out my numbers so that my graph isn't super condensed. In your domain, we should label number of tickets. The range are your y values, and we have to go from 0 all the way up to 63.80. So for that case, I think I'm going to jump up by tens. So we'll do 10 and then 20, 30, 40, 50, 60, 70, 80. I didn't label each one just because it'll get a little bit messy. And this would be our cost of the tickets in dollars. So let's do our best to graph this. When you purchase 0 tickets, you spend $0. 1 ticket is $15.95, so that'll be approximately there. 2 tickets, $31.90, so a little bit above the 30 mark. 3 tickets, $47.85, so just below the 50 mark. 4 tickets, $63.80, so just above the 60 mark. And I would not draw a line connecting these because, like we already stated, our domain is discrete and we cannot purchase a fraction of a ticket. We are going to skip over the on your own section only because these video notes will be too long. Example 4. A bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. The first question asks, does this situation represent a linear function, and explain? When you think about this, we have the number of bars eaten and the number of calories consumed. As you eat one bar, you consume 130 calories. You eat another bar, it's another 130 calories. So this is a linear function. Yes, it's linear because the rate of change is constant. For every bar, it's 130 calories. Find the domain of the function. Is the domain discrete or continuous? So the domain, I want you to think about it. Would it be discrete or continuous? Discrete means we would have to only eat one bar and then two bars and then three bars. If it was continuous, the domain is the number of bars eaten. So that means that we could eat a fraction of a bar, 2.5 bars, or 1 3/4 of a bar. Is that possible? Yes. So the domain is continuous because you can eat a fraction of a bar. All right, so for letter C, you're going to graph the function using its domain. So we have the input values B for the number of bars eaten, and we're going to have the output values C's for the calories consumed. So if you consume or if you eat 0 bars, you're going to have 0 calories. If you eat a bar, you will consume 130 calories. If you eat 2 bars, your calorie count will be 260. 3 bars, your calorie count will be 390. And finally, 4 bars, your calorie count will be 540. I'm sorry, 520. Ordered pairs, list X, then Y. So 0, 0, 1, 130. In this case, instead of X, comma, Y, it would be B, comma, C. Those are your X and Ys. And then we have 2 bars, 260, 3 bars, 390, and finally 4 bars, 520. And when we graph these, we should label our axes. The x-axis would be number of bars consumed or eaten. And your y-axis would be calorie count. And for the numbers of bars eaten, we're going from 0 to 4. So once again, I can make 0 here, and then I can spread this out and have 1, 2, every 2 lines, 3, 4, and the last one's 5. Just make sure, a common mistake I see, a lot of students might start with 0 and then they'll put 1 right here and then they'll start skipping 2. That's not okay. If you're going to skip 2, you have to skip 2 right away. Okay, for the y-axis, we have to go all the way up to 520. So I'm thinking that maybe if we go by 50s, every one is 50. So if I go up 2, that's 100. If I go up another 2, that's 200. Go up 3, that's 300. Up another 2, 400, and the very top line is 500. We have to go to 520, but we can make it work. So the first ordered pair is 0, 0. 1 goes to 130, so above 100, below the 150. 2 goes to 260, so we go to 200, and then a little bit above the 250 line. 3, we're just below 400 at 390. And then 4 bars, we're going to be above 500, about there. So because this is continuous data, we can connect these to make a straight line. And if you eat 2.5 bars, you can say, oh, my calorie count will be somewhere around, according to this graph, around 325. And if you were to plug that in, calorie equals 130 times 2.5. If you were to put that into a calculator, you actually get 325, which the graph shows pretty accurately. Step 3 says draw a line through the points, which we already did. And then they want you to start at 0, 0 and continue to the right and use an arrow. So we're going to put an arrow there to say that the more bars you consume, the higher your calorie count will be. This concludes the notes for section 3.2.